So we are now up to step 5 of workshop 4. So we have explored the changing the effective sample length and how that has an impact on what our average is, how long your data set is, and now we need to look at how changing the sample rate, so how many times per period we sample, or how quickly we sample our data, and what that means in terms of the final output. And one of the issues that can occur is that we get this problem of aliasing. So step 6 is to demonstrate the issue of aliasing, which is actually a byproduct of undersampling our data. We go back to our lecture slide on aliasing. So aliasing occurs when your sampling rate is too low. In other words, the time between successive samples is too long in order to pick up the periodic components that you're looking for, and you end up with a period which looks like it's much longer than it really is, or that one exists. So, for example, in this time series, artificial time series here, so just a simple sinusoid, we can see that this red line up to this point represents a full wave period, and while we have a sample at the very beginning of that wave period, we don't actually sample, we don't take another observation, we don't record another data point until into the next cycle of this wave. So it's a bit like trying to record tidal elevation over a longer than a tidal period. So every 13 hours, say, if you record the tidal elevation, then you're not going to get the semi-diurnal tidal signal, are you? And so then we're going to try and illustrate that with our data, because we have got tidal data. So let's just get rid of that. Okay, so we are going to try and change the sampling rate in our data set, but what we have to be aware of, first of all, is that it is already a discrete data set. It's already been sampled, tidal height's obviously continuously varying, but it's already been sampled at 96 samples per day. So we are already limited by the resolution of the data set we're given. So if you recall, our time interval between successive data points was 0.0104 days, okay, and which equated as a sample rate of 96 per day, and that gave us a sampling interval of 15 minutes, okay, which is the same thing here in days. So we multiplied this number by 24 hours per day and 60 minutes per hour, and we got 15 minutes. So the time interval is 15 minutes. So that means that our time, the longest period that we could observe would be 30 minutes. Oh no, yes. Shortest period that we could observe would be 30 minutes. So what that means is that we wouldn't be able to see waves, for example. So if there's wind waves with periods of, like, I don't know, 15 seconds, then you wouldn't be able to pick that up in the tidal time series that we've got. And it might just be useful at this stage, actually, just to plot our time series as a set of data points. So rather than drawing a line between them, let's just have a look at the data points themselves. So if you recall, we had actually interpolated this data. So if we just plot that as data points, it might look a bit messy to start with. I don't know where the figure is. That's one with the gaps. Okay, so it's coming out here. It's at the bottom. Okay, I'll just generate a new figure. And plot that one again. Okay, so this is with the data points in it. Okay, now this time series obviously is quite long. We don't need to see 200 days worth, so let's just have a look at a shorter time period. Okay, we've got days on the y-axis, so let's look at just 1 day. Okay, and then we'll limit our title height from 0 to 7, so we've got the same y-axis limits. Okay, now you can see the samples that were actually recorded. Okay, now what we want to do is, we can't sample faster than this, but we can undersample. So we could pick every second data point, which would give us a sampling rate of 48 samples per day. Okay, if we sampled every second data point. If we wanted to sample, say, twice a day, we'd have to sample every 48th data point. So we'd take the first one and then the 49th one, and then we'd add another 48 on top of that, okay? And that would give us 2 samples a day. So effectively what we're doing is we're multiplying, so say our time interval in days, and we multiply that by the sampling rate. And that tells us how many data points we need to skip. So like I said, if we want to sample at an interval t_int is equal to half a day, so t_int is equal to 0.5, then we would want to sample our time series. So we can just plot it actually. If I hold that figure and then we plot on top of that, and we want to pick out those data points that are occurring at half-day intervals. Okay, then we would have, we want to start from, so TD1, start at the first data point, and then we want to skip half a day times 96. Okay, so we want to skip and take every 48th data point. So 0.5 times 96. Okay, and we want to might as well go to the end. So the final, we're not plotting it anyway, hopefully it'll keep the axes limits where they are. And then we'll do that for pick out the same indices in our title height, which goes from 1 to 0. So half a day intervals times 96 samples per day up until the end. Oops. And I'm going to make those into little red circles. And so hopefully, mismatch something here. What have I done? Oh, I haven't put a brackets around the end here. Okay. Each one. So I think that should be okay. Yeah, okay. So you can see what's happened here. Great, we're only sampling every 48th data point, which gives us 2 samples per day. Okay, that's moving on to the first point of the second day. And clearly we're not picking up that periodic component. So that's the kind of thing that we're going to explore. So it would be quite nice if we had a little subroutine to do this, or write a little script. Okay, so let's generate a script called subsample.m. Yes, we want to create it. Okay, so this is a function, and we want it to output a subsample time series, TSS, call it YSS, and our function's called subsample, and we're going to pass it a time and a Y, and we're also going to pass it a time interval. Okay, let's write out what this does. So this function subsamples a regular time series y t at a time interval t int. Okay, so first of all we need to find out what the input sample rate is, but we already know that actually is just 96 samples per day, but assuming we have a different sample rate, let's so find the sample rate of input. Okay, so you might recall we find the sample rate is just 1 over the time interval between samples. So the time interval between samples, we can choose any 2 consecutive indices of our time axis. So T2 minus T1, that'll be fine. And then our sample interval is just 1 over del T. And you might recall that because we were getting decimal places and because we're using the sample rate as an index, we just knocked off those decimal places just so that we know we've got an integer. Okay. So we want to output a subsampled time series, and going back to what we just looked at here, you can see that when we plotted samples at intervals of half a day, we multiplied that interval, half a day, 0.5, times the sample rate per day. Okay, so that means that we were skipping over every 48 data points. So instead of having 0.5, we could put in t int, and instead of having 96, we could put in our sample rate, fs. Okay, so going back to our editor again, then we can assign our subsample time series then. So we're just picking out, so in other words, the data points are there, we're just not using all of them. So we are going to subsample from 1 and skipping every t int times fs data points until we get to the end of that array. And then we do the same thing for our y variable from 1, and then we skip over t int times fs up to the end. Okay, and then we can plot that. So let's generate a figure, plot t comma y. So and what we want to do is try and generate a figure that demonstrates what happens if you were to join up all these subsampled times. Okay, so plot that and then hold on, and then we want to plot on top of it our subsample time series y ss, and let's use red circles that are joined together with lines. Okay, hold off, and then let's put a legend in here as well, because we've got 2 time series. So we've got original first, plotted first, and then we have so we just generate a string now because we're going to resample it at different ones. Resampled, and this is where we can stick in the time interval. So we want to convert that number to a string, num to a string of t int. So what that means, it will concatenate this string resampled with the string equivalent of t int, and t int is in days. Okay, so our time is in days. Should probably put that up here as well. Regular time interval of t int days. Okay, and then x label time in days, and y label water elevation in meters. Okay, I think that looks okay. So save that. Right. So explore the sample rate of our time series by subsampling our data set at varying time intervals. So we're going to try inputting varying time intervals and just see what happens. So we've written a function that subsamples our data set. Okay, well, let's just have a look at it. We have to pass it time, then our y-axis variable, and then we have to pass it the time interval in days. Okay, so let's try 1 day, for example. So t int is equal to 1. Let's just try 1 every day, see what happens. That means we get an output of td subsampled and h1, I can't be bothered to write the whole thing out, let's just call it h subsampled. And we want to call that function, and we're going to pass it td1 and h1 new, and we are also passing it our time interval. Okay, what are we missing? When calling a function or indexing a variable, use parentheses. So somewhere in here, subsample line 18 colon 55. So always read the little expression or the error message, that because it's usually very helpful. So somewhere in line 18, I have probably missed out brackets, yes, because this is not linked up with anything, is it? To try and work out which ones are paired together. This is the problem, the bracket's on the wrong side, I think. Yes, okay, so you can see it just paired up those brackets now, so that should be fine. Okay, so use parentheses, mismatched, that's what happened here, we've mismatched delimiters. Okay, so let's try that again. Seems to be working okay. Let's make this bigger. Okay, so right away you can see we are definitely not picking up the periodic components that we would expect to see. And by undersampling, which is, you know, dropping from 96 samples a day to only 2 per day, we are not seeing the tidal the semi-diurnal tide at all, which we wouldn't expect to, but also it's picking up a much longer time period signal here. Okay, so let's try a different one. How about if we sample for longer? So let's try t int is equal to, I don't know, 7 days. Okay, and then we'll run that function again. So it looks even messier. Okay, so you can see how by undersampling our time series, we are basically seeing the phenomena of aliasing, whereby it appears there are longer periodic components available than they really are. Okay, we could try a shorter time interval. Let's try t int is equal to, what should we try? A quarter of a day, 0.25. Okay, and what does this do? It's looking slightly better, but maybe we'll change the time axis on that. Let's do 10 days. Okay, so at a quarter of a day, you can see that, so it's every 6 hours, it is starting to pick up, but that's kind of at the limit of the sample rate. Okay, it's starting to sort of flatten out here because we're not actually picking up, because of the phase difference, we're not actually picking up the peaks and troughs so regularly. So it only really works when it becomes in closer to the same phase as the tidal height data. Okay, so that's when we're sampling it very close to the limit. Okay, so in terms of your follow-up work then, if we go back to our worksheet, okay, so you should demonstrate the issue of aliasing. So this was when it was resampled at 0.5 days and changing the time axis there. So for your coursework, the task 4, do the same thing but use a different year. So you have to try and find a time series which has got a sufficient length to it without a large gap, because as you might recall, the time series of 2012 had a larger gap beyond, I can't remember, around 300 days or something, and that's very difficult to fill in that gap. So you need to work with a time series that has sufficient length and not so many gaps that you can't effectively interpolate them. Okay, so you should produce figures of the interpolated time series, which was basically what we did here. Choose in step 3, choose a section of the time series, write a function to fill in any missing points, and we plotted it up to check that it looked okay. And then produce figures of the interpolated time series. That was A. B. Plot the cumulative mean, which is what we did in step 4. Okay, write a script to find and plot the cumulative average, and then show some examples of aliasing. Okay, so you can choose whatever time intervals you like, but the idea should be to demonstrate choosing a time interval which is not sufficient to observe the periodic components that exist, and that actually indicates periodic components that do not exist, which in this case here is that this very long period signal, which is not really there at all.